Untangling the Tangled Cloud. I'm Joshua Fox, Senior Cloud Architect from DoiT International. And what I do in my job is advise technology companies, whether it's in Google Cloud or AWS. I have a bunch of certifications in both of those. And I'm also, by the way, a Google developer expert, which means I travel the world, talk about Google technologies. This talk is about Google Cloud, AWS, but really the principles are general. They could apply to any cloud and, in fact, any system. But the example we're taking is Google Cloud projects and AWS accounts as an organizing principle. Do you face this? Cloud resources, hundreds of them, databases, queues, virtual machines, cloud functions, lambdas, this massive number, and you look at them and you have no idea how to sort them out, no idea who's responsible for them, or how to work with all these resources. What do you do when you have all these resources? In today's talk, you will learn how to sort out your cloud resources in whatever cloud, how to put them in order, how to understand where they are so you can more efficiently manage them. And during the talk, I'll define what I mean by managing them and the benefits you get by untangling them. How we will solve this problem? By looking at dependency graphs. So we will see what a good dependency graph looks like. Of course, I'll define what it means for things to depend on each other. And the boundaries should enable a good dependency graph. I said untangling the tangled cloud. If you think of things connected to each other, you want the boundaries should be drawn in a way where that's not a tangle. You'll come away with this with 7 mental models for organizing the cloud. Now, these are principles that I learned during my 23 years of experience as a software architect, mostly in product development, rather than SRE or customer reliability engineering. So these are principles I didn't invent myself. But they're short phrases, concepts, where you recognize a situation, you say, oh, that's what we need to do here. Now, if you're experienced, you've probably heard of many or most of these, in which case, congratulations, that's good. But remember, everybody has to learn each concept anew from when they're born. So there'll be many people here who have not heard all these concepts, and if so, take them with you, because they are useful to many situations in organizing your systems, whatever they may be, here specifically referring to cloud resources. Towards the end, I'll present an open source tool that I developed, and I enjoy doing that. The value it gives is that it proves the concepts. Technology makes guesswork real. So people may have thought in the past about what it means to fly, dragons, and of course we saw real birds, and maybe angels. But only when you have a real flying aircraft can you see most clearly that you truly understand the aerodynamic principles. It's a flying proof that you understand that your science is correct and brought down to earth. So I'll show you this software tool that measures how tangled your cloud is, the quality of your Google Cloud projects, and gives real numbers that can help you understand what the problem is and perhaps even the specific areas that most need improvement. So I was inspired in building this tool by another tool. This is 25-year-old open source software used for Java code development, a different area. And it's pretty amazing that it's still a brilliant and useful software tool. Now, we here are focused on SRE, not software development, but I will present that to you for a few minutes because it's so great and because the principles do carry over to the cloud as I redeveloped it for this other space. The way I met Usenix is through this article, which you can get that bit.ly address or scan the QR code. In the end, I'll show you an easy way to get my slides too. And this article actually is the same content as today, but today's talk is in much more depth than the article in the Usenix login publication. What my customers struggle with. Let's talk about some case studies for a Tangled cloud that is causing great trouble to the customers that I advise. My customers at DoiT are all technology companies, leading edge digital natives. Some of these use cases, though, apply more to legacy companies, which I do have some experience working with as well. Population bomb. Several thousand virtual machines in a single AWS account. And that means they had to ask for a quota increase. It all started with several simple applications. There was no need to create multiple AWS accounts. And over time, these applications grew. They grew vertically, which is actually easy, because if you have an auto-scaling group, automatically scales up. You don't have to think about that. That's actually one resource conceptually. But also horizontally, as new microservices, we're at a new database, new analytics, new queues. So now there's this gigantic AWS account with all sorts of things in it. Lambdas, databases, applications running on virtual machines. No one has a clue. So that's one use case. So that slide's out what I do. I advise tech companies. We're actually a cloud reseller. They buy AWS and Google through us, but then I also advise them. And moving on to another case study, which is the opposite of the first one. Every developer is an island. Lots and lots of AWS accounts. So a company starts with the goal of giving each developer their own space, their own playground, which makes sense. It gives them responsibility, and they can do whatever they want in there. They don't have to step on anybody else's toes. But now, each developer has an account, also QA, staging, production, and some of their projects came into production use. So a developer develops something, now it's running. You can't just shut it down. It's not just a playground. It's not just for development. So instead of having, as I said earlier, one gigantic AWS project, you now have many small projects. Another case study. I call this the estates because each team has their different area of ownership, the database team and the application team running on virtual machines and the analytics team that may be using Kinesis for processing, message queuing is another space because the message queue connects everything together. And this is more common in on-premises systems like banks that have the database team. And kind of an old-fashioned attitude. Unfortunately, as they move into the cloud, because of organizational structure, they often have the same way of working in the cloud. But really, it doesn't work because that application needs to connect to that database, and now two completely different teams need to talk across organizational boundaries. So that, even though it looks well organized, does not do it either. How does it hurt? Earlier I said difficult to manage, but let me count the ways. Let me explain the trouble you're in this case where your cloud resources are not well organized. Cost analytics. So you have all these costs. This is actually, DoiT has a cost analytics tool for the cloud, but it doesn't help to know that you have, maybe there's a database running on that virtual machine. Who uses that database? Who connects to it? Who's responsible? Which budget does it need to go to? We have something called attributions, which mean to attribute the cost to some cost center, but how do you attribute it? You need some way of being able to tell which team gets it in their profit and loss calculations, or simply which manager needs to be told to control that cost. So you need to somehow arrange those. Network security. Now, we all know that we have to draw our virtual private clouds with subnets, and there needs to be a good logic behind that. For example, often subnets are, in a typical web application, front end, back end, database subnets. And there are other levels of organization. AWS network firewalls can draw a boundary that's even greater than that. So that's great, but only if you know where the boundaries go between the systems. Typically, a VPC includes an application. What does that mean? So you need to know how to sort it out in order to achieve network security. IAM security, identity and access management. We group our people into groups, so developers, QA might be a couple of groups, but we also need to bundle the resources into groups to say the developers can access this and the finance team can access that. What are the groups of resources? So you can think about this in terms of the people, the group of people accessing, but also machines accessing each other. That could be in Google Cloud, that's called service account. In AWS, it's called role, a confusing word. So both humans and machines need to contact these bundles, but you don't know what the bundles are. They might be defined as technical, under technical concepts, or under a business unit. Another pain point, dealing with change. So what happens when an API changes? This here is a trivial example where a birth date is no longer an age, which is a number, but rather now a birth date, which is a string in a date format. Okay. And of course you use semantic versioning so that you can track the different versions as it changes. But changing every client application to use a new version is impossible if you don't know what the client applications are. There could be 100 of them. You don't know. What is accessing what? You want to control that, not just for security, but for change management. Finding the impact of a change in your API. DevOps. When you give commands, you want to give commands to a reasonable set of resources at a time. If we have all these virtual machines that are being upgraded from one version of Debian to another, you probably don't want to upgrade all the VMs that have a single purpose because you want your system to stay live, but you do want to, I don't know, upgrade half of them at a time. But which are they? And the VMs that exist now are in different versions themselves. Some have already been upgraded to version 10. Some are version 9. You need to give commands that act on a reasonable unit, and to do that, you need to even know what the unit is. If there's a bug, and you're starting to guess that maybe it has to do with the version of Debian that is running a certain application, you have to even know where to look for that. Okay, that was very painful. Now, let's talk about what a solution looks like. You draw your boundaries for these units in a way that enables an untangled graph of dependencies. So I'm not going to ask you to change your application. That's almost impossible when you're in DevOps. If one microservice calls another, that's still going to happen. But you as an architect need to think in advance, but also think after the fact about what units do call one another, and then draw the boundaries. And of course, I will make this more formal later. I'll explain exactly what this tangling or untangling looks like and how it's defined. So again, your goal is not to rebuild your applications, but to define boundaries that reflect your applications. We'll focus on a case study for the rest of the lecture. This is a more detailed case study of an e-commerce company that got its act together. And we'll use this for our examples. So we have a front-end PHP web application calling out to Java Spring Boot microservices. And there are typical units here in the system. One thing I should say is that these names are not accurate because it's not built. The boundaries are not drawn correctly. That's what I'm talking about today, right? But anyway, if you were to ask them, they'd say, oh yes, these are the microservices, more or less. In reality, they would have more confusing names because nobody really understands. But let's imagine this to keep ourselves focused, that we even understand what we're trying to do here as we build this. And the dependency graph here is bad. One thing that you can immediately see is that there are cycles. And there are other things I'm going to define later beyond cycles. But As you know, the problem with a cycle is that it forms a single closed unit. When A depends on B depends on C, and C depends on A in a circle, any change in any one of those could impact every one of those. And that's why cycles are bad. So this is the system that we have and the boundaries that are drawn at the beginning. And after re-architecture, the boundaries define a beautiful directed acyclic graph, and everything is very clean with the minimum dependencies and more metrics to be discussed later. And now those names are meaningful. They make sense. I've been saying boundaries over and over, but boundaries can be defined in different ways. So what tools can we use to define boundaries? It's anything that bundles cloud resources into a higher level. Microservices, applications, whatever you want to call those. And technically, we can do it in different ways. In Google Cloud, we use projects. Google Cloud makes it very easy to create new projects, and the projects themselves are bundled into folders, folders into other folders, into organizations. Very neat. We're not going to focus on organizations now, other than to know that typically you work completely within one organization, not two, not three. It's your company. But we're going to focus on the projects and how they relate to each other. Out of today's scope, I'm not going to talk about, but it's defining different projects for QA, staging, development, production. Very important, and it's a concept, but that actually is kind of easy to understand, so we'll take that into account, but we're focusing more on the different applications rather than the different levels of the environment. And all these concepts are general. I'm talking about tools like Google Cloud Projects, but there can be smaller boundaries. I talked about VPCs. It could be just conceptual. You have an architecture diagram. You say, these things form a unit. Of course, it's useful to have tools that strongly enforce those boundaries. AWS has something called accounts, and a bit different from Google Cloud Projects. They're conceptually a bit harder to create new ones, but you can. It doesn't cost anything. And the accounts can be linked into something called an organization. Works differently from Google because AWS added it a few years later, so it's not quite as structured as a hierarchy, but our concern today is accounts as a unit of organization. The advantage of using projects or accounts is that they already enforce many of the points I said earlier. There is no network connection between two AWS accounts unless, of course, you define it. They're not part of the same VPC, obviously. Or IAM is defined on the level of the Amazon account, the Google project. There are different levels, but that's the basic level where it's defined. So already it's saying, these are your boundaries. You are sure of that. Nothing is sneaking in there just by accident, by default. So these are useful tools to use for that. Azure is something I know about less. At DoiT, we have some Azure, but a lot less than of the other two. But you can do the same thing. Resource groups are a useful way to bundle resources into groups because the people at Microsoft thought of the concepts actually, probably the same ones I'm talking about today. There are also other levels for organizing information. Subscription is more for the user who created a resource. A management group is something on the level of organization where you're managing IAM and policy and compliance for multiple subscriptions. Just to show you that the concepts are general, and this is also cloud, Kubernetes is another level on top of the cloud. It almost reproduces many cloud concepts within the scope of a cluster. And you can live in this new world, which lives on top of the cloud level. So you could have different namespaces in which all the pods, all the deployments dealing with buyers are in one namespace, sellers, shopping cart, and namespaces can be a separating. It's not quite as default a separation as you get between Google Cloud projects, but similar. And you could even create different smaller clusters, which is a useful way of defining groups for isolation. Blast radius, reducing the blast radius, a little bit more cost efficient to have a large cluster. Another way of organizing is with labels. Now, labels are useful because you can add them after the fact. I think they're probably not what you want to use because it's too much information. These can be called tags, labels. Don't have to worry about the exact terminology now in the different clouds, but they can be used for network control from the Google firewall. They can serve for IAM. You can define Amazon IAM saying you're allowed to access the ones with this label, not the ones with the other label. However, these are not hard boundaries. By default, it doesn't enforce anything. It completely depends on you. They're very unstructured, so you can have overlapping values as opposed to those neat hierarchical structures I showed earlier where a project is bundled into a folder in Google, for example. Each label is its own dimension. Region, tier, business unit. Each one is a different label key, which organizes things. Which one do you choose to use first? This is one of those mental models, one of these concepts that's been very useful to me, is the notion that when you have multiple dimensions of organizing things, then it can be hard to decide which goes first in sorting things out. I don't know anything about the US military, but they have Army, Navy, Air Force, Marines. But you say, well, they're almost like four separate, completely separate armies. You say, well, don't they cooperate with each other? So yes, there are these geographical divisions worldwide, and then they bundle together parts of those different Army, Navy, Air Force, Marines in that geo division. To take an example that's more from our area of experience, as a manager, the old way of doing things was to have a marketing department and then developers, product managers, and each one has their own, executive running them. But more recently, the concept is cross-functional units. So you have the ones developing the games, and that contains marketing, developers, product managers together. And that means they can be focused on their mission, which sounds good. It means, though, that there's no marketing executive. Well, there probably is a marketing executive, but not one who is completely in charge of the marketing people under a separate scope. So you have two different dimensions here. Which one comes first? That's the difficulty, and with labels, that gets out of control. So that's why I wouldn't use labels. How do we draw the boundaries? First of all, let's talk about what can go wrong. The mega blob, I mentioned this briefly earlier. So this is tempting. You have a project, and it often happens as you grow from zero, as you just get more and more things in your little startup that started with, one virtual machine, and now it's got so many. And as you move quickly and grow quickly, you forget to define the boundaries and create a new AWS account or Google project. There are no boundaries here at all. The little projects often happens when that developer who had control of the one project or AWS account now has a small team, and they're in charge of some great software. But the boundaries now are defined according to historically who founded the team. And as they move on, you get lots and lots of projects. It is just the same as the other example because there are also no boundaries. Yes, there are boundaries, there are projects, but imagine in the limiting case that every single resource had its own AWS account. There's no boundaries there. The account boundaries are useless. And this micro boundaries can also increase costs because you cannot share resources. Every team here has to decide for themselves, there's always some wastage for themselves, perhaps pay for Amazon support, and therefore that's another disadvantage. So that's what's bad. Now let's talk about what's good. Let's talk about how you resolve the problem. The first guideline always, follow the business. Melvin Conway is an engineer's hero. He was not an MBA. He was a software engineer who invented, I think, coroutines. And he said, Conway's law, organizations which design systems are constrained to build systems that follow those same organizational structures. So if your team has one group in Ukraine, one in Boston, they cooperate, they work together, but as you build out the systems, you will have two separate units. this will happen. You have no choice. He's not saying you should or watch out. No, that will happen. It is an iron law. So your first principle is to make the architecture follow the organization. As you graph it out, as you think about it, just realize the architecture will look like that. But if you are a manager, then of course you should also think about the organization following the architecture. You build them both together. And not just arbitrarily because you happen to found offices in 2 different cities or because there were 2 managers who needed their own domain. Think about the organization as well. So in order to find the graph technically, we spoke about the business, but technically we have to also consider the boundaries. To do this, we define the dependencies. The definition of dependency is that B depends on A if any change in A can make B fail. That's it. More specifically, a dependency occurs when one cloud resource calls another API in another cloud resource. And you can often track this in Google by looking at which service accounts are allowed to call resources in another Google Cloud project. There are other cases, though. For example, if 2 units talk to a third, let's say we have one AWS account that defines a schema, and then in a third project, and then another AWS account also uses the schema. So even if they don't talk to each other, the fact that the one defined the schema impacts the other. If the schema changes, it will crash. A callback is saying, A says to B, please invoke me, please call me back. So now in the future, even though it's actually B calling A still has a dependency because it expects to be called with this callback. If that changes, its behavior will break. The concept of a dependency is very general. In Java, it could be importing a package. In Python, it's libraries that actually the word dependency is used for those. And even a class that calls a method from another class. Or a function that calls another function. Anything where a change can make it break and is a dependency. We need to minimize cycles and create a directed acyclic graph. We already explained why that is. It turns separate units into a single unit. Because one thing here in this diagram breaks, warehouse breaks, and then orders and users potentially can all break. So in our e-commerce company, when they sorted it out, this is a directed acyclic graph. And of course, if some of these things break, it will break others. Users is a very basic concept for authentication. So if the user system is messed up, everything else can go down. But the front end getting messed up shouldn't crash our authentication system. Next principle, and this is one of those mental models, one of those key thoughts to have in everything you do in life, is low coupling, high cohesion. So to look at this abstract graph here, taken from Wikipedia, on the one side we have, on top, it's the way it should be. As you see inside each box are a number of dots that talk to each other, they relate to each other. They're in the same box, they belong together. Meanwhile, between the boxes, there's a very little linking. There's that one green line. So, highly cohesive inside the unit, but low coupling between the units. The bad example down below is that the dots inside a box don't really talk to each other that much, so why are they together? And then in between the boxes, there are lots of those red lines, high coupling. So that's the abstract concept here. And if you have lots of these links, it's not just that it's a graph, it's cyclic or acyclic, but rather just the fact that these cloud units, these Google Cloud projects, talk to each other too much. You want to avoid that. They should talk to each other minimally. And as this architecture was reworked, the amount of coupling was reduced. Remember, reworking the architecture doesn't mean that things should not invoke each other. Yes, they have to invoke each other. It means that units, cloud systems that invoke each other should usually be inside the same Google Cloud project or AWS account. Cohesion. Here you have orders, virtual machine, database together, which makes sense, but then the shipping DB is in there too. And if we saw earlier the example of a bank that had moved from on-premises to the cloud, all their databases are together. The databases don't talk to each other. So the things that talk to each other should be together. Shipping compute and users compute don't belong together. The shipping DB belongs with the shipping compute. And so draw the boundaries. I don't mean draw the boundaries so that the things that talk to each other, this is of course a highly simplified example, go together. I said that we should have low coupling, high cohesion, but what should depend on what? This is all about what changes and what doesn't. Another mental model is that your job as an architect is to know in advance what will change and what won't. How can you know the future? Well, that's why you're paid those large salaries. So a user-facing application changes often, because who knows, in this restaurant they're going to change the menu, change the look and feel. So that's probably will change often. But the database hopefully will not change that often. It has to be stable, and you don't want to lose referential integrity. So that's an example of something that should be stable. This is the nostalgic old tool that I mentioned, JDepend. I won't go into too much detail about that because this is not primarily a developers conference, but it is cool. It's from, I don't know, 1998 or something. And it actually measures dependencies on Java packages. What Java class imports another Java class? That's their idea of this arrow, of this dependency. It has two types of arrows, inbound and outbound. So inbound is, coupling is sometimes called afferent, from Latin ad, like advent, afferent. Don't worry about that, think of it as inbound. And this is the dependee, the thing that is depended on. We see here the orders with that red circle. Orders is depended on by front end. Front end depends on orders. So that's one type of link, which we count those inbound arrows. The other type is outbound, efferent, like exit. It's not a Latin class, but efferent coupling is the opposite of afferent. And think of it as outbound couplings. These are the dependents, the things that depend. So front end, that red circle means it depends on other things, and that's what we're counting. Instability, for some reason Mike Clark, the inventor, counting instability rather than stability, is the out arrows over the total number of arrows. And remember, the database, the infrastructure should be stable. The front end may be unstable. That's how it should be. Is it? Well, that's why you have the tool. And just as a very simple example, orders has 2 out, 1 in. So you have 2 divided by 3. And that's the level of instability of the Java package, which is called orders in this case. Imagine this is a single code base, monolith, not a microservice. You have all these Java packages. There's some other things that only apply to code, but an abstract class like vehicle is very basic, but then when you develop a subclass Maserati, there can be lots of new car models. The concept of the vehicle will not change. And so Mike Clark says that the more abstract a package is, the more stable it should be. And this graph measures the notion that abstractness and stability should be tightly correlated. But getting back to a concept which is relevant to the cloud, dependency cycles can be measured between Java packages. So in this case, I looked at the Apache Commons imaging package, where it only measures links inside a single software library, just as in the cloud, you only measure links within your organization. We're not talking about links from outside, that's another story. And not under your control in that way. So afferent couplings, and then it measures the instability of within the imaging. That's the base package, the one that should be stable. So low instability. Meanwhile, JPEG is just one specific example. Tomorrow they can invent new ones. I keep forgetting JPEG X, JPEG 2000, all sorts of WebP. So that's unstable. These things can change, and in fact, it does have a higher instability. It has fewer inbound and more outbound couplings. And it measures cycles in the same way. It says, this is a cycle from a thing to itself, which is of course fine, but also file filter. That's okay, it's one cycle. But, Okay, that was Mike Clark, or his open source project, Clarkware, JDepend. I created a new tool for the cloud, Ferent. You've seen all the principles already. I wrote it for a large company, for thinking about several large companies, much messier than this. This is just what I could fit on a slide. But imagine lots of Google Cloud projects, all sorts of resources calling each other. What's going on? Just as an architect, you can't even understand what is dependent on what. And we're going to focus on just a simple example where the front end, as we know, can change, and users, which involves IAM, authentication authorization, really should not be changing. It should really be stable. The output of the Ferent tool is to just look at a very simple stripped-down example. The front end is unstable. Nothing depends on it. Good, good. No one likes something to be unstable, but things do change. Nothing depends on it. Meanwhile, users is pretty stable. So it's measuring the dependencies between Google Cloud projects. In a minute, I'll tell you how it does that. This is the output. It ran over 44 projects. I actually tested it in our systems and DoiT. We have thousands of projects, but, and, oh no, there's a cycle. That's not good. One project depends on another, which depends on the first one. You as an architect want to know that. And it's measuring specifically Google Cloud projects, not AWS accounts. That's another tool if somebody wants to write it. It's also not measuring many other ways that you can define boundaries, Kubernetes namespaces, etc. But Google Cloud projects. How do we know that one Google Cloud project depends on another? After all, if it invokes an API. But how do you know it invokes? You're not going to track the packets in the network. So we look at permissions. This microservice is associated with a service account, which in Google is like a user, but not a human user. It's the service itself, the cloud function, the virtual machine, which has an identity, which is a machine identity, the service account. And our concept is that we're going to count how many permissions have been granted. In this example, permissions to the user's project. In this example, the shipping Google Cloud project has been given permission. This one service account is given permission. Storage object viewer, it doesn't really matter the exact permission. Meanwhile, the orders project, 2 permissions have been given. This service account and this service account, 2 permissions. We're measuring those arrows, service account permissions. You might ask, is this a fair assumption? Is this a good way to measure dependencies between Google Cloud projects? Well, think about it. Internal authentications, I hope, are going to be authenticated. That's how modern cloud systems work. Actually, on-prem in the old days, you could trust that you were inside your own private network. It's just not how you do it in the cloud. You authenticate internal integrations. And to do this, you use service accounts. That's just the way it's done. If you don't want to use best practices, well, that's on you. But this is the best practice for Google. Very similar in Amazon, by the way. And preferably, we use one service account per application. If I have 2 different applications, then that's 2 different service accounts. If you ignore that and just use one service account for everything, actually this will still work. It just won't count how many permissions were given to a project. It will say orders, as I said, it was given 2 different permissions to users. It'll just treat it as one. It will still measure the fact that one project depends on another, just not how much. And you can see the Git repo here. Yes, please, I love my code. Scan that, you can get the slides afterwards as well. It was written in Clojure. I love Clojure. If you've ever studied Lisp, whether in university or for fun, that's great, I wish I could do that. But everybody in the industry says, oh, you can't use Lisp, it's impractical. So Clojure is based on the Java virtual machine. It is used in practice, in production, by many leading companies. I'd like to thank Jonathan Shavit, who mentored me through this. He's a Clojure expert. You can Google him too, read his excellent articles. And that code may not be familiar to you if you're experienced with Python or Java, but I learned it and I enjoyed doing so. Clojure is on the Java virtual machine, so it integrates with the Java APIs, as you see here. That is simply a Java API. That's it. It's not a Clojure API. It is invoking search projects response to count the projects, and it just works with Java. It also works with the command line, very clean integration. I call gcloud command line tool to understand the organization in this case. You run it like this. The key point here is that you can filter out projects because typically an organization may have thousands of projects starting SYS, which are app script. Google, Workspace, G Suite, app scripts, you filter those out because they're just not relevant to what you're doing. So as we see here, it measures these projects, and getting back here again, this is the output. It counted which projects are dependent on which projects, and therefore it can tell you if there are cycles. It can tell you if the things that should be unstable are unstable. If you were to see that users, for example, had a very high instability count, you'd say, whoa, something's wrong here. And you would fix it, hopefully. Key takeaways. Just to summarize some concepts that you learned. Your job, the thing you're paid for as an architect, is to know what will change and what will not. That is difficult. Next concept is order of dimensions and branching. You have to decide which dimension wins, which dimension is the one used for ordering things, and which one gets pushed down to second place in the tree, in the hierarchical organization. These are all principles, the principles I'm saying now, that apply to life in general. This is life philosophy. But, of course, I'm talking specifically about the cloud today. Conway's law, your architecture will follow the organization. There is nothing you can do about it. So think about that when you create either the architecture or, as a manager, when you create the organization. Cycles are bad. Make directed acyclic graphs. Again, a very general principle. The reason it is so general is that cycles make things into closed units with each other. Next principle, low coupling, high cohesion. Things that are together should talk together, otherwise why are they even together? Things that are separate should talk to each other minimally, because that's what it means for them to be separate. And stability should correlate to the amount of inbound dependencies. So something that you just know is unstable can depend on other things, but don't make anything depend on it, because when it's unstable, it will make them crash when it has changes. Meanwhile, rock-solid things are the ones that can be dependent on the things that will not change. So I enjoyed talking to you today, and now we have a few minutes for questions.